Hello and welcome to this video tutorial where we're going to cover dead reckoning and the dead reckoning and GPS correction component. Now what we have here, I'm just going to open up a data file to show you. This is the data we're going to be operating on using Framework4 today. And as you can see, it has accelerometer components, magnetometer components and GPS already synchronized into the software. Now what we also have is video data as well, which we've recorded for ground truthing purposes, and this contains latitude and longitude components, and we're going to use this today to correct our dead reckoning path we obtain. So I'm just going to load up this data now. And it's a CSV file. Select CSV, click import, and we're going to take the headers from the file. So it's imported our headers as they were specified in the CSV. Now if I go into Framework4, I can visualize the accelerometer channel, for instance, just to see that everything's loaded correctly. But in this tutorial we're going to be using the dead reckoning wizard, which is under the tools menu, and we select dead reckoning to open this up. Now there are a number of options we can use to perform dead reckoning. Firstly, we have the alignment. So what we found was that in some devices the coordinate systems can be offset, so the accelerometer coordinate system may not be pointing in the same direction as the magnetometer coordinate system. So we perform alignment, and we need to calculate the heading, calculate the speed either by using vector or a constant speed, and then we want to tie in together the speed and the heading to utilize dead reckoning to get a trajectory out, and then finally using the dead reckoning and GPS corrections. So if I click next, we go on to the alignment. I know that this specific data set was face down, and after I click next, it's going to take us to the compass correction settings. Now magnetometer readings, or rather the Earth's magnetic field, which is what they measure, can be permeable to hard iron and soft iron deposits, which can mess up the heading. So we utilize a correction algorithm for this, which is based on ellipsoid fitting, and you can read more about this in our paper, but essentially it's applying a correction matrix to each of the compass components. So click next, and it's going to ask us for the pitch and the roll. Now the compass coordinate system needs to always be level with the Earth's surface in order to be able to obtain a correct heading. So what we need to do is we need to compute the pitch and roll to sort of negate this offset, or rather perform tilt correction to correct the compass coordinate system so it is back to level with the Earth. So click next on this, and our heading is computed. And as you can see, this has gone through a variety of different angles here, and in fact this was me walking around in a field going around in rectangles, so you can see that by the sort of step up and step down in the angles. Now if I click next, it asks us for the VEDBA. I can just click compute on this. I've got the accelerometer components there, but one of the things that we can also do in here is, if I have data labeled, I can select behavior based VEDBA and select the behaviors in here, and it only computes the VEDBA for these behaviors. Okay, so finally it takes us to the dead reckoning page, and this is going to ask us for a start latitude and longitude, which I have recorded down. Okay, and if I click compute on here, I know this was offset at 90 degrees. I'm just going to put a small little speed coefficient on here. Okay, so we've obtained our trajectory as so. As I said earlier, this was me walking around in the field, and we have a number of parameters here. So for speed, we're using VEDBA. We're using the heading derived using the previous components. We can identify a start index, so if I started at 1000, it's going to start at data item 1000 as opposed to 0. We apply a heading offset to orientate the path in the right direction, and this is based on the angle of declination. A speed coefficient multiplies the VEDBA via this, so if I increase this now to say 0.1, you can see the path is becoming longer and more stretched out. We find that around 0.3, 0.4 seems to work well for humans, but this could be obviously any value. And finally we have a speed threshold here where if the VEDBA falls below this value, it's going to be automatically zeroed out. But this path is looking quite good. I'm happy with this, so I'm just going to click next and continue. And we're taken to the dev reckoning and GPS correction page. And if I just add our dev reckon path on here, you can see that. And I'm going to add our video data in here. Actually, we're not going to use the GPS, we're going to use the video just for the purpose of this. So what I can do is I can add the video data, and this is exactly as it was specified, and I can change the resolution of this, so I can say select meters and only use a fix every 2 meters, 3 meters, just zoom out a bit here, try and center it, there we go, every 4 meters. So you can see the path is becoming less and less fine detail, it's becoming less granular, and as so. What I can do here is we have this correction loop where it's using every fix in the GPS or video data as ground truth, and it's going to force a dev reckon path through this. So if I apply our correction loop, one iteration, apply distance correction here. So the green path here represents the GPS and dev reckon correction path, and you can see it's sort of tied in some of the features from the dev reckon path along with the ground truth fixes we've used, and you can see it's not quite as angular, it's filled in the gaps. Now if I click next on this, what happens is the data gets appended to the end here, so we have our corrected latitude and corrected longitude, which we can use in other studies. If I click finish, I can go into visualization, click on the path view, select to add a path. In this case we're going to add the one we just computed, the corrected latitude and longitude. I'll click add, and this is added as so. And what I can do is I can play back through the data to watch it over time. And I'm just going to add the video, just for example, and that's in blue. So we can see it only used a fix every, I think it was 4 meters, but actually it's come out with quite an accurate path here. Okay, so that concludes performing dev reckoning along with dev reckoning GPS correction. Thank you very much for watching.